there is something fundamentally broken about the road beneath your wheels. In 312 BC, Roman engineers began construction on the Via Appia, a highway stretching from Rome to Brindisi, a distance of 350 miles. That road, built over 2,300 years ago, with nothing but stone, gravel and lime mortar, is still drivable today. You can walk on the original paving stones, feel the grooves worn by centuries of cartwheels, and marvel at a surface that has survived the fall of empires, barbarian invasions, and 2 millennia of weather. Now look at the highway outside your house. It was repaved 5 years ago, maybe 10. Already you see cracks spiderwebbing across the surface. Potholes appear every winter. Edges crumble. Asphalt patches fail within months. Your city's transportation department has a permanent repaving schedule because modern roads are built to fail. The average American highway needs major resurfacing every 7 to 12 years. Some sections need repair every 3 to 5 years. We spend over $100 billion annually just maintaining roads that are designed to deteriorate. Meanwhile, a Roman road built when Julius Caesar was a child is still carrying traffic. What did Roman engineers know that our modern highway departments have forgotten? The answer isn't that they had better materials. The answer is that they built roads as permanent infrastructure, not temporary patches. And the 4-layer system they perfected is so superior to modern asphalt that it's almost insulting that we call what we drive on paved roads. Before we go deeper, hit that like button and subscribe to the channel so you don't miss what's coming next, then drop a comment and tell us. How often does your local highway get repaved? Have you hit a pothole that damaged your car? How much have you spent on tyre repairs and alignment because the roads are falling apart? Let us know, because what you're about to discover will make you furious at what we've accepted as normal. The modern failure. Roads built to crumble. Pick any major highway in America. Interstate 95, Interstate 10, the 405 in Los Angeles. Now look up how much your state spent repaving it in the last decade. The numbers are staggering and the results are pathetic. California spent over $2.3 billion on highway maintenance in 2022 alone. Texas allocated $1.8 billion, New York $1.5 billion. These aren't one-time expenses. They're annual budgets dedicated to patching, resurfacing, and rebuilding roads that were finished less than a decade ago. And despite these billions, the roads keep failing. Modern roads are asphalt, a petroleum byproduct mixed with aggregate and laid in thin layers over compacted dirt. It's cheap to install, fast to lay down, and designed with a planned obsolescence that would make a smartphone manufacturer jealous. The typical asphalt road consists of maybe 4 to 6 inches of blacktop over a base layer of gravel or crushed stone. That's it. No deep foundation, no structural integration, just a thin band-aid of tar stretched over dirt and called infrastructure. And it fails predictably. Asphalt melts in summer heat, literally. When temperatures exceed 140 degrees, which happens regularly on sun-exposed highways in summer, the asphalt softens. Heavy trucks press into this softened surface, creating ruts and depressions. These ruts collect water. In winter, that water freezes, expands, and cracks the pavement from within. This freeze-thaw cycle is the death sentence for asphalt roads, and it happens every single year in 2/3 of the United States. But here's where it gets worse. Asphalt is porous. It looks solid, but it's actually full of microscopic voids where water infiltrates. That water doesn't just sit on the surface, it seeps down through the asphalt, penetrates the base layer, and erodes the soil underneath. As the base erodes, the asphalt loses support. It flexes under traffic loads. Flexing creates cracks. Cracks allow more water in. More water means more erosion. The cycle accelerates until you have potholes large enough to swallow a tyre. The industry claims this is good enough and cost-effective. They'll show you charts proving that asphalt has the lowest upfront cost per lane mile. What they don't show you is the life cycle cost. When you're repaving the same stretch of highway every 8 years at $1 million per lane mile, the math stops making sense. A 10-mile section of highway costs $10 million to repave. Over 50 years, that's 6 or 7 repaving cycles. You're spending $60 million to $70 million on a road that never stops needing work. Now contrast that with Roman roads. The Via Appia, Via Flaminia, the Via Aurelia, roads built between 312 BC and 100 AD, using a 4-layer system of foundation stones, gravel, concrete and fitted paving stones. These roads required virtually zero maintenance for centuries, not decades, centuries. The Via Appia has sections outside Rome that haven't been touched in 1,500 years and are still smooth enough to drive on. Tourists walk on them, cyclists ride on them. In some areas, cars still use them daily. Modern engineers will tell you this is impossible with today's traffic loads. They'll claim that Roman roads worked because they only had wooden carts and foot traffic. This is a lie. Roman roads carried endless streams of loaded wagons, each one weighing several tons when fully loaded with grain, wine or stone. They carried entire legions of soldiers, tens of thousands of men marching in formation with full packs, armour and equipment. They carried merchant caravans, livestock, siege equipment and the constant traffic of the world's largest empire for over 500 years of peak use. And they didn't fail. The difference isn't traffic. The difference is engineering philosophy. Romans built roads to last forever because they understood that infrastructure was the foundation of civilization. Every road was a permanent investment in the empire's future. Modern governments build roads to last until the next budget cycle, because infrastructure is a political talking point and a revenue stream for contractors. We build roads to fail on schedule so someone can be hired to fix them. Again, and again, and again. The Roman road system covered over 250,000 miles at its peak. Much of it is still there, buried under fields or incorporated into modern roads. The portions that remain exposed are still functional after 2,000 years. The highway outside your house will need repaving before your car hits 100,000 miles. That's not progress. That's engineered failure. The investigation. The 4-layer Roman system. To understand why Roman roads never die, you have to dig down, literally. Archaeologists excavating Roman roads have found a construction system so sophisticated that modern civil engineers are forced to admit we've regressed. In 2014, a team from the University of Cambridge excavated a section of Roman road near Pompeii. What they found was a masterpiece of engineering that puts our modern highway system to shame. The Roman road wasn't a surface. It was a complete structural system that went down 4 to 5 feet into the earth. Each layer had a specific purpose, and together they created a road that could handle any load, any weather, and any test of time. Layer 1. Statumen. Romans excavated down to bedrock or compacted virgin soil, sometimes digging trenches 8 to 10 feet wide and 3 to 4 feet deep. Then they laid large foundation stones, some weighing over 100 pounds each, fitted tightly together. These stones were sometimes 2 feet thick, creating an immovable base that distributed weight across the entire road structure. Modern roads skip this entirely. They scrape off topsoil, compact the dirt, and call it good. When the soil settles, and it always settles, the road above it cracks and fails. Layer 2. Rudus. On top of the foundation stones came a thick layer of gravel mixed with broken pottery, crushed stone, and sometimes crushed brick, compacted into a solid mass 12 to 18 inches thick. This layer served 2 critical functions: drainage, and flexibility. Water flowed through this gravel layer out to drainage ditches on the sides. Ground movement and temperature changes were absorbed here before reaching the rigid layers above. Modern roads have a similar gravel base, but it's typically only 4 to 6 inches thick and poorly compacted. It doesn't drain properly and doesn't absorb stress. Layer 3. Nucleus. Here's where Roman engineering becomes almost magical. They laid a concrete layer 12 to 18 inches thick made from lime, volcanic ash called pozzolana, and sand. This combination created a substance harder than modern Portland cement. It was waterproof, load-bearing, and permanent. Once cured, Roman concrete didn't deteriorate. It got stronger with age. Modern roads rarely use concrete bases in highway applications. When they do, the concrete is thinner, lacks the volcanic ash chemistry, and still cracks within decades because the base wasn't properly prepared. Layer 4. Summa crusta. The surface was cut stone, usually basalt or granite, shaped into polygonal blocks that fitted together like a puzzle. These stones were cut so precisely that a knife blade couldn't fit between them. No mortar needed. Each stone was slightly cambered, higher in the center than at the edges, creating a crown that shed water immediately. A loaded wagon rolling over these stones transferred its weight directly into the concrete layer below. The stones never flexed, never compressed, never wore down beyond surface polishing. Basalt has a compressive strength of over 30,000 psi. These stones could support any load the ancient world could produce. But the real genius was the camber. The entire road surface was crowned in the middle, typically rising 6 to 12 inches higher at the center than at the edges. Rain hit the road and immediately flowed to the sides into carefully graded drainage ditches that carried water away from the road structure entirely. No standing water meant no freeze-thaw damage, no erosion, no weakening of the base. The road stayed dry, and dry roads last forever. Modern roads are flat or poorly graded. Water pools on the surface, seeps into cracks, and freezes in winter, expanding with 9% more volume and blowing the pavement apart from within. This is basic physics. Water is the enemy of every road ever built, and the Romans solved this problem 2,000 years ago with simple geometry and proper drainage. We've forgotten this, and now we spend billions patching roads that water destroys every single winter. The knowledge was never lost. We just stopped using it. The chemistry. Why Roman concrete outlasts everything. Here's where it gets fascinating. Modern concrete is strong, but it deteriorates. Bridges built in the 1950s are crumbling. Highway overpasses from the 1970s are being demolished and replaced. Yet Roman concrete structures are still standing after 2,000 years submerged in seawater. The Pantheon's dome, poured in 126 AD, remains the largest unreinforced concrete dome in the world. Harbour breakwaters built by Emperor Claudius are still intact underwater. What's the difference? Roman concrete used volcanic ash, specifically pozzolana, from the region around Mount Vesuvius and the volcanic fields near Rome. When mixed with lime and water, a chemical reaction occurred that modern scientists are only now beginning to understand. The volcanic ash contained aluminum tobermarite, a rare mineral that forms naturally in the mixture over time. This mineral actually makes the concrete stronger as it ages, the exact opposite of modern concrete, which weakens and deteriorates over decades. Research published in 2017 by the University of California, Berkeley, analysed samples of Roman maritime concrete from breakwaters at Portus Cusanus that have been underwater for 2,000 years. They found that seawater reacting with the volcanic ash created interlocking crystals of aluminum tobermarite that filled microscopic cracks and made the structure denser and more durable over centuries. The concrete was literally healing itself, growing stronger through the same environmental exposure that destroys modern concrete. The lead researcher, Professor Marie Jackson, stated that Roman concrete undergoes a continuous recrystallization process when exposed to seawater. Minerals in the seawater react with the volcanic components, forming new binding compounds that reinforce the structure. After 2,000 years of wave action, the Roman samples were found to be more cohesive and crack-resistant than freshly poured modern marine concrete. Modern Portland cement, invented in the 1800s, is faster to set and easier to work with, but it lacks this self-healing property entirely. Worse, it's porous. Water infiltrates microscopic cracks, and in modern reinforced concrete, that water reaches the steel rebar inside. Steel rusts when exposed to moisture and oxygen, expanding to roughly 3 times its original volume. This expansion creates internal pressure that cracks the concrete from within, a process called spalling. Within 50 to 100 years, most modern concrete structures show significant deterioration. Roman roads didn't use steel reinforcement because they didn't need it. The concrete itself was structurally complete. The volcanic ash created a chemical bond so strong that the cured concrete became effectively monolithic, a single unified mass rather than aggregate held together by a binder. This is why Roman concrete doesn't fail at the joints or crack along stress lines. There are no weak points, but the real genius was in the paving stones themselves. Basalt and granite are igneous rocks, volcanic in origin, with compressive strengths exceeding 30,000 psi. These stones are nearly impossible to crush under any load the ancient world could produce. Asphalt, by comparison, has a compressive strength of around 500 psi. It's not even in the same category. When a loaded truck drives over asphalt, the material deforms under the weight. It compresses, creating ruts that become permanent depressions. Over thousands of passes, these ruts deepen, water collects in them, and the road fails. When the same truck drives over fitted basalt stones, resting on Roman concrete, the load is distributed across the entire stone and transferred into the concrete layer beneath. The stone doesn't deform, it doesn't compress, it doesn't wear. It simply transfers the force downward into the foundation, which was built to handle it. This is engineering that works with physics instead of fighting it. You don't try to create a surface that resists compression. You create a surface that doesn't compress at all. You don't try to make concrete that resists water damage. You make concrete that uses water to grow stronger. And it lasts millennia because the materials themselves are nearly indestructible. The Romans weren't lucky, they were right. The proof: roads that refuse to die. Let's talk about the Via Appia, because the evidence isn't theoretical, it's still there, and you can drive on it today. The Via Appia, begun in 312 BC by Appius Claudius Caecus, remains one of the most important roads in Italy. It was called the Regina Viarum, the Queen of Roads, and 2,336 years later, that title still holds. Sections of the original Roman paving are still intact and still in use, not preserved behind barriers in a museum. Actually in use, carrying bicycles, motorcycles, and even cars on stretches where local authorities permit it. In 2019, researchers from the Polytechnic University of Milan conducted structural analysis on a 15-mile stretch of the Via Appia near Rome using ground-penetrating radar and core sampling. What they found should embarrass every modern highway engineer. The road's load-bearing capacity exceeded modern highway standards. The foundation showed zero settling after 2,300 years, meaning the road sits at exactly the same grade and elevation it had when originally constructed. The drainage ditches on either side were still functional, still channeling water away from the road structure. The paving stones, though worn smooth by millions of footsteps, cartwheels, and centuries of use, were still interlocked and stable. No cracks in the concrete layer beneath, no erosion of the foundation, no structural failure of any kind. Compare this to Interstate 95, the main highway running along the US East Coast from Miami to Maine. Built in sections from the 1950s through the 1980s, I-95 requires constant maintenance, perpetual repaving, and continuous repair. A 2018 report by the American Society of Civil Engineers gave US roads a grade of D+, noting that 43% of public roadways are in poor or mediocre condition. The economic cost of driving on these deteriorating roads, vehicle repairs, tyre damage, fuel waste from congestion, exceeds $130 billion annually, or more than $500 per driver. The average service life of an asphalt highway before major rehabilitation is needed, 15 to 20 years under ideal conditions. In areas with harsh winters or heavy truck traffic, that number drops to 7 to 12 years. Some urban highways in northern states need sections repaved every 3 to 5 years just to remain safe. The Via Appia has gone 2,300 years without major rehabilitation, and it's still structurally sound. Then there's the Appian Way's sister roads, the arteries of Rome's empire. The Via Flaminia, completed in 220 BC, still carries traffic from Rome to Rimini, a distance of 210 miles. Long sections retain their original paving. The Via Aurelia, running along Italy's western coast toward France, was built in 241 BC and remains a major route today, with Roman foundations still supporting modern traffic. The Via Egnatia, stretching 696 miles from the Adriatic coast through Greece to Byzantium, was completed around 146 BC. Parts of it are still used as the primary road through remote, mountain regions of Albania and northern Greece, all built between 300 BC and 100 AD, all still partially intact and functional after more than 2,000 years. Archaeological excavations along these routes consistently find the same thing: roads built so well that even neglect, war, and abandonment couldn't destroy them. When the Roman Empire fell in 426 AD, maintenance on these roads stopped. No one repaired them. No one cleaned the drainage ditches. Vegetation grew over them, yet they survived another 1,000 years of the Middle Ages as the primary transportation network of Europe. Modern highways fall apart if maintenance stops for 5 years. Roman roads survived a millennium of zero maintenance and were still functional enough to be incorporated into medieval and modern road systems. That's not ancient luck. That's engineering superiority so profound we still can't match it with all our modern technology. The modern disconnect. Why we chose failure. So why did we abandon a road building system that worked for 2,000 years? The answer has nothing to do with engineering and everything to do with money and speed. The shift happened in the early 1900s with the invention of the automobile and the rise of the petroleum industry. Suddenly, nations needed thousands of miles of roads, and they needed them fast. Asphalt is a byproduct of oil refining. Essentially, it's what's left over after gasoline, diesel, and other valuable products are extracted from crude oil. It's the bottom of the barrel, literally. The oil industry needed a market for this waste product, and road construction provided the perfect solution. Asphalt was cheap, abundant, and could be laid quickly. A Roman road took months or even years to build. Excavation, layering, stone cutting, concrete curing, paving stone placement. An asphalt road could be paved in weeks. Pour it hot, roll it flat, open it to traffic the next day. For a nation like the United States building the interstate highway system in the 1950s and 60s, 41,000 miles of highway in just 35 years, asphalt was the only option that could meet the timeline. Speed trumped everything, but the decision was never about durability or long-term value. It was about speed and upfront cost. A Roman-style road costs significantly more to build initially. Deep excavation down to bedrock or compacted subsoil. Multiple compacted layers of stone and gravel. Thick concrete made with specialized volcanic materials. Cut and fitted paving stones. Labor-intensive doesn't begin to describe it. An asphalt road costs a fraction as much to install. Just scrape, compact and pave. The problem is life cycle cost. When you factor in repaving every 7 to 12 years, annual pothole repairs, traffic disruptions, lost productivity from construction zones, vehicle damage from poor road conditions, and the economic drag of unreliable infrastructure, asphalt becomes astronomically expensive over time. A study by the Texas Transportation Institute found that a typical mile of highway costs $2.5 million to $4 million to build initially, but requires $8 million to $12 million as in maintenance and repaving over a 50-year lifespan. That's 3 to 4 times the initial cost just in repairs. A Roman-style road might cost $10 million per mile to build using modern equipment and techniques, but would require virtually zero maintenance for centuries. Over a 100-year period, the Roman road is 5 to 10 times cheaper. Over 500 years, there's no comparison. The ROI is obvious, but it requires long-term thinking that modern government budgets don't allow. Politicians operate on 2-10 to 4-year election cycles. They want ribbons to cut, projects to announce, and their names on plaques. A road that takes 3 years to build doesn't get you re-elected. A road that requires no maintenance for 200 years doesn't generate headlines or photo opportunities. Contractors want repeat business. A road that never needs repair means no future contracts, no ongoing revenue, no guaranteed work. The construction industry has a vested interest in infrastructure that fails on schedule, and the asphalt industry has lobbied for decades to ensure their product remains the standard, funding research that emphasizes upfront cost while ignoring life cycle analysis. Meanwhile, your tax dollars are poured, literally, into roads that melt in the summer, crack in the winter, and need replacing before your car loan is paid off. State DOTs know asphalt is inferior. Engineers know it. But procurement systems are locked into lowest bid contracts that evaluate only initial cost, not 50-year total cost of ownership. Roman engineers built for their civilization's grandchildren. They designed roads that would serve the empire for centuries, understanding that infrastructure was the foundation of prosperity and military power. We build for the next election cycle, the next quarterly earnings report, the next budget justification. And we wonder why our infrastructure is crumbling while Roman roads that carried chariots still carry cars. Practical application. How to build roads that last. If you want roads that don't fail, you have 3 options. Demand better, build smarter, or accept that we've chosen a system designed to waste your money. Let's break down what actually works. First, at the policy level, cities and states need to stop optimizing for upfront cost and start calculating life cycle cost. This isn't complicated math. A road that lasts 200 years without maintenance is dramatically cheaper than a road that needs repaving 15 times in the same period. Engineers know this. Accountants know this. Transportation planners know this. But procurement systems are designed around initial bids, not long-term value. The contractor who submits the lowest bid wins, regardless of whether that road will last 10 years or 100 years. This needs to change. Bid requirements should mandate life cycle cost analysis. A proposal should include projected maintenance schedules, expected service life, and total cost of ownership over 50 or 100 years. When you run those numbers honestly, Roman-style construction wins every time. Some municipalities are starting to get it. a few forward-thinking cities have begun requiring 50-year cost projections in infrastructure bids. The results are telling. Suddenly, higher quality construction methods start winning contracts because the math finally reflects reality. Second, for new construction, incorporate Roman principles using modern technology. Deep foundations that reach stable soil or bedrock. Proper drainage with cambered surfaces and engineered runoff systems. Multiple compacted layers that distribute loads and prevent settling. Durable surface materials that don't deform under traffic. Modern technology makes this easier than ever. We have GPS-guided excavators that can grade to millimetre precision. Hydraulic compactors that can compress base layers to densities Romans could only dream of. Diamond blade stone cutters that can shape basalt and granite faster than a Roman mason could chisel sandstone. We could build roads with Roman durability using modern efficiency, and some places are already doing it. The Netherlands has experimental roads using layered stone and concrete systems inspired by Roman engineering. After 20 years, these roads show near zero deterioration. No cracks, no settling, no maintenance required beyond occasional cleaning. Germany has similar projects in Bavaria, where engineers combine traditional stone construction with modern materials, science. The data is clear. It works. These roads cost roughly 2.5 times more to build initially, but have required less than 5% of the maintenance costs of comparable asphalt highways. Third, for private roads, driveways, and small-scale projects, you can apply these principles yourself. This is where individual property owners can opt out of the asphalt trap entirely. Excavate deep, at least 18 to 24 inches, more if your soil is unstable or clay heavy. Lay a foundation of large stone, 6 to 8 inches thick, compacted until it doesn't move under your weight. Add a layer of compacted gravel, 6 to 8 inches, for drainage and flexibility. Pour a concrete base, 4 to 6 inches thick, using a mix with high compressive strength. Top with fitted pavers, cut stone, or even reclaimed granite blocks, arranged with a camber so water sheds to the sides. The upfront labour is significant. This might take you weeks instead of a weekend. The material costs are higher. Stone and concrete cost more than asphalt. But the result is a surface that will outlast you, your children, and possibly your grandchildren. No resurfacing, no patching, no annual repairs. Just a driveway that works permanently. The Romans didn't have machinery, GPS, hydraulic compactors, or diamond blade cutters. They had knowledge, patience, and a commitment to building things that would last. We have better tools than they ever dreamed of, and we're building roads that fail faster than ancient civilizations with hand tools and ox carts. That's not progress. That's regression disguised as efficiency. If you're tired of roads that fail you, if you're ready to demand infrastructure that actually lasts, hit that subscribe button and that like button. We're exposing the forgotten engineering that modern industry once buried. Share this with anyone who's ever hit a pothole and wondered why we can't build roads like we used to. Because we can, we just choose not to. The Roman engineer surveying the route of the Via Appia wasn't primitive. He was a master of applied physics, hydrology, and materials science. He knew that water is the enemy of any road. He knew that load distribution requires mass and incompressible materials. He knew that proper drainage and camber prevent 90% of road failures. And he knew that building it right the first time was cheaper than rebuilding it every decade. We traded that wisdom for petroleum byproducts and quarterly earnings reports. We built roads designed to fail so contractors could be hired to fix them, so asphalt plants could sell more product, so politicians could announce infrastructure investments every election cycle. And now we drive on crumbling highways, dodge potholes, and pay taxes for endless repaving, while Roman roads built before Christ was born are still carrying tray tick. The knowledge wasn't lost, it was abandoned. And every time a city chooses to build with stone, concrete and proper engineering instead of cheap asphalt and prayer, they prove the Romans were right. Roads can last forever. We've just decided they shouldn't. Subscribe and let's keep digging up what they buried.